And yeah, and then those views that you compute, you basically you export that data into a database that you can query. So, for example, we wrote a database called ElephantDB, where you can export data in batch to it, and then you have this distributed database that you can query in a key-value manner. So, you know, this all sounds really good, right? It's just you write these functions that take the whole data set as input, and then you have a view. Like, that's about as easy as you can get, right? You can compute anything that way. So, in practice, and you may have suspected this, it's too expensive to always recompute every view from scratch just to get, like, you know, just to add in this little bit of data that you've gotten since last time you computed the view. So in practice, what you do is you add the minimum amount of incrementalization necessary to get the performance you need, right? So at BackType, like, a full recompute for us might take like a week, but we've added enough incrementalization that we can consume new data, update our views in only a few hours. Right, so in reality, a batch workflow looks something like this. You have, you know, on the bottom, you have your master data set, which is all the data. And then on the left, you have kind of new data that you haven't really consumed yet. Then you have this batch workflow that consumes that new data, and then it updates your batch views. That's called view maintenance when you're updating a view rather than computing it from scratch. Right, and then at the end, it'll then append that new data that it finished consuming back to the master data store. So the cool thing about what I've described here is that this batch layer I've described satisfies every property we care about except for low latency updates. So it's robust and fault tolerant. So it's robust and fault tolerant to machine error just innately because it's using a fault tolerant distributed computation framework like Hadoop. And it's also robust to human error. So, you know, the algorithms you use are these recomputation algorithms that kind of just take in your raw data and produce some output. So if you were to do something like, say, deploy the wrong algorithm that then corrupts your batch views and puts a bunch of bad data in there, well, you have a clear path to recovery, right? Just fix the algorithm and recompute the views, and you're fixed. Likewise, if you write a bunch of bad data, right, like data that's just bad, and then that corrupts your views, well, to fix it, well, the master data set is append only, so you didn't lose any of your previous data. So you just go to your master data set, you filter out the bad data you wrote, and then you recompute the views, and everything's fixed. Clear path to recovery. This supports low latency reads, right? Those batch views are indexed and queryable. It is scalable to increases in data or traffic. Like those batch views, like those like ElephantDB that we have, it's very easy to scale by just adding more machines. Likewise, Hadoop is very easy to scale. You just add new machines, and it gets used automatically. This is very easily extensible. So once you have the batch workflow set up, the master data store set up, all you have to do is add a new view, and then you'll have, you know, whatever new feature that view will support. And since this thing is all based on batch computation, right, like the first time, let's say you add some new feature, but you have all these existing features, well, the first time you add that feature, you do this full recompute, and then you put it into your incremental batch workflow, and it gets updated. So, you know, what I've described is clearly general to diverse types of data and requests. Like, you can't get more general than this model of arbitrary computation on arbitrary data. You know, it naturally allows ad hoc queries. So you're using Hadoop, so you can do arbitrary jobs and explore your data set. Or you can run a Hadoop job to sample your data set and then explore it, maybe on a single machine. Minimal maintenance, like, you know, the only system you really have to worry about is Hadoop, which honestly does require some knowledge to operate correctly, but that's really the only system you have to deal with. And it's the only system that you have to understand and get functioning, and then everything else just works on top of it. Right? And finally, a system like this is debuggable, right? Since we have, like, you know, I call it a linear flow of data. You always have your inputs, and you always have your outputs, right? So if some value gets corrupted, then you can look at, okay, what was the input data that caused this output value, which is weird and unexpected? And then you can understand, okay, what caused this problem? But like I said in the beginning, this does not satisfy low latency updates. Fundamentally, batch computation is high latency. So we're going to have to do something to fix this. Okay, So this is where the speed layer comes in. And the speed layer exists solely to compensate for the high latency of updates to the batch layer. It's a separate system we'll build, and its only purpose is to kind of fix that problem. And a key point that kind of makes all this tie together is that the speed layer only needs to compensate for data that has not yet been absorbed into the batch layer. So if your batch layer takes 6 hours to run, then that means there can be at most 12 hours of data not represented in your batch views. So the speed layer only needs to compensate for those 12 hours of data. Any other data is in your batch layer. Right? So this means your speed layer only needs to deal with hours of data instead of years of data. And this is great. This is great because the speed layer, as we'll see, is going to be significantly more complex. So the fact that it has to deal with just a small amount of data makes it significantly easier to build and gives you a lot of flexibility. And basically what you have is you have your batch layer producing some pre-computed views, and you have your speed layer doing something, producing its own databases or views. And then when you want to actually see what the value is for a view, well, you query the batch layer, you query the speed layer, you merge the results together, and now you have a real-time view that operates on however many terabytes of data you have. So like I was saying before, the speed layer is all about just doing things to compensate for however many hours of data are not in your batch layer. So once the data is in the batch layer, you can discard those results from the speed layer. You just constantly have this result which is compensating, and then you throw it away in a few hours when it's not needed anymore. So the speed layer is interesting in that batch processing is relatively understood. There's a lot of people working on it, a lot of companies using Hadoop. The speed layer, there doesn't really exist yet any general model of computation for the speed layer. So generally what people do now, and I think this is going to change, but what people do now is you end up building these message passing infrastructures. So a lot of people will say, this is using the model of computation called stream processing. So in batch computation, you kind of do these big computations on these big fixed-size data sets, whereas in stream computation, you kind of have this one stream, this one infinite stream of messages, and your goal is to process every message one at a time and as fast as possible. So generally what people do now is you use queues, so like RabbitMQ or Kestrel. There's a variety of queues, and then you'll have some series of workers that pass messages to each other that will process the messages and update some database somewhere. And in the speed layer, you tend to use highly incremental algorithms because you need the speed. So whereas in the batch layer, we do these recompute style algorithms. So to do a count, maybe you just get all the items and literally count them. Whereas in the speed layer, you would do something like, when you get a new message, increment some counter somewhere. That's an incremental algorithm. And in the speed layer, you can use a variety of databases. They tend to be traditional read-write databases. So the scalable ones that are well known are things like React, Cassandra, HBase. But since you're dealing with only, let's say, 12 hours of data, you have the flexibility to use MySQL even if you want, or Tokyo Tyrant, or some other database that isn't necessarily horizontally scalable. So as I was saying, the speed layer is significantly more complex than the batch layer, just because you have to deal with message passing and more complex algorithms and more complex databases. But the batch layer is constantly overriding the speed layer and kind of replacing whatever the speed layer is computing. So all that complexity in the speed layer, which is by far the most complex part of your system, is transient. It is constantly going away. So if you mess up how the concurrency works, or you have some problem in how it's working, that's okay because the batch layer corrects the speed layer. And this property gives you a lot of flexibility in how you build your algorithms. So one common thing you do to get a real-time complex algorithm going on big data is that in the batch layer, you might do some slow but really accurate algorithm, something that does a lot of intense computation. Because ultimately, the batch layer has the time to do these intense computations. Then in the speed layer, you may do the algorithm in a different way. You may do it in this fast way, but you may use this approximate algorithm, or just some hack to just get it fast, something you wouldn't be able to do otherwise. And since the batch layer is constantly replacing this results from the speed layer, you get this property, which I like to call eventual accuracy in your system. So as like an example of like a situation where you might use an approach like this, let's take a simple example like computing, like a BackType example, computing the number of unique people who have tweeted out some domain. Right? So on the batch layer, what you would do is that whenever you want to update that count for a domain, you would go ahead and get all the people who have tweeted that domain, you'd unique that set, and you'd count them. Right? So you'd get an exact result. This is a little bit harder to do in the speed layer because if you get a new person, like a new tweet that has tweeted some domain, it's not necessarily reasonable to go get a set of like 2 million people and then add this person to the set and then update the counter. So what you might do in the speed layer is use something called a Bloom filter, and a Bloom filter is essentially a compact set that sometimes has false positives. It's this probabilistic data structure, right? But it's compact, right? So it's much easier to deal with in this incremental approach. So in the speed layer, you would check the Bloom filter and say, okay, has this person already tweeted this domain? If they haven't, then I'll increment the counter. If they have, then I won't do anything. And of course, the Bloom filter will sometimes have false positives, so you'll have some inaccuracy in your results. But that's okay, because the batch layer corrects the speed layer, so you still have this eventually accurate approach. I still have 21 minutes. I thought this would take a lot longer to explain. But I do have some additional things I can talk about in case I ran short. So the other thing I want to talk about is what kind of data model do you use for like a system like this, right? I think everyone here is probably used to like the relational data model, and you have primary keys and rows and tables.